Hello there and welcome to our help video over 9-6 mole-to-mole conversions. As we take a look at 9-6, we realize that we have a combustion reaction of benzene. And they give us the formula of C6H6, which is a hydrocarbon. In Unit 8, we learned a combustion reaction. We'll have this hydrocarbon burned in the presence of oxygen. And our products are carbon dioxide and water. And in order to balance this, we would go straight up Hollister. We've got 6 hydrogens here, so initially we would try to put a 3 there, but 3 would be an odd number. And we can't have an odd number in front of the water because that would give us an odd number of oxygens, which is impossible. Hollister says do hydrogen first, carbon second, oxygen third. We double that 3 to a 6. That gives us 12 hydrogens. 6 times 2 is 12. So we would have to put a 2 in front of this. 2 times 6 hydrogens is 12. That also gives us 12 carbons. 2 times 6 is 12. Carbon would be next. Hydrogen first, H. Carbon second, C. We go 12 in front. 12 times 1 is 12. And now we are on our third and final element in this reaction, oxygen, HCO. We have 12 times 2, 24 oxygens, plus 6 times 1 is 6. 24 and 6 is 30. So we need a 15 in front on this side to have 30 oxygens. Balancing is very important because we are doing mole-to-mole reactions. Mole-to-mole is an important calculation. It is one of the most fundamental calculations that are a part of so many problems that we call stoichiometry. Stoichiometry is using chemical equations to provide as the backbone for many types of calculations. So here's our chemical equation, and in this first problem, how many moles of water would be produced? So we're looking for moles of water. How many moles of water would be produced from burning 3.5 moles of benzene? This is a mole-to-mole. They are asking for moles of one thing, water, and they're giving us moles of another, benzene. Remember, when we do these kind of problems, the moles of what we're given go right here to start the problem off with. As our given, our question is, we lead the whole problem off with our question, how many moles of water? Question mark moles of water. So right here we have question mark moles of water, and there is our given. Now, what is it that relates moles of water to moles of benzene? That would be the chemical equation. So we come up here. There are 6 moles of water, 6 for every 2 moles of benzene. 2 goes there. We can write this equality. This is an equality that comes from the chemical equation. And we can write any equality 2 ways. We can put 6 moles of water over 2 moles of benzene, or we can put 2 moles of benzene over 6 moles of water. When you have 2 things that are equal, you can always put one over the other in either order. So those are our 2 conversion factors. You'll recall, whatever we're trying to find, moles of water must be on top. The moles of benzene, C6H6, must go on the bottom. So we need this conversion factor right here so that the moles of benzene cancel out. Mole of benzene divided by moles of benzene cancels out, leaving with moles of water. So we have 3.50 times 6 divided by 2. That's 10.5. In our second question, they want to know how many moles of oxygen would be consumed in the process of burning 3.5 moles. So we're burning the benzene in the presence of oxygen, and we're burning 3.5 moles of benzene. They want to know how many moles of oxygen we would need. So our question goes first, question mark, moles of oxygen. Our given goes right after the equal sign. Our given's 3.5 moles of benzene. We go up to our equation. We would see it's 2 moles of benzene for every 15 moles of oxygen. That's an equality. 2 to 15. 2 to 15. This is an equality from the balanced chemical equation. Now we want to express this as a conversion factor. We can put 15 moles of oxygen on top, 2 moles of benzene on the bottom. Or we can put 2 moles of benzene on the top, 15 moles of oxygen on the bottom. Those are the two ways that we can express this. We need to pick one of those two because we're trying to convert moles of benzene to moles of oxygen. So I need the one with moles of oxygen on top. I need moles of benzene on the bottom so that they cancel out. We want the moles of C6H6 to cancel out. 3.50 times 15 divided by 2 is 26.2, which also happens to be the official distance of a marathon. Has nothing to do with the problem. Next question. How many moles of carbon dioxide would be produced in burning 3.5 moles of benzene? So we go back up to our equation. This time they're wanting to know how many moles of carbon dioxide would we get in burning 3.5 moles of benzene. So our question mark is question mark moles of carbon dioxide. We're still burning 3.5 moles of benzene, C6H6. Where do we get the equality 2 moles of benzene for every 12 moles of CO2? Right here. 2 moles of benzene for 12 moles of CO2. That is an equality. We can write that two ways. We can put the 12 moles of CO2 on top and the 2 moles of benzene on the bottom, or we can put the 2 moles of benzene, C6H6, on top and the 12 moles of CO2 on the bottom. You can always write an equality with either one on top and the other one on the bottom. Here we go. Which one do I need? I'm trying to find moles of CO2. So that unit is going to have to be on top. I'm starting with moles of C6H6. I need the one with that on the bottom. So I come right over here, and there it is, 12 moles over 2 moles. Now you want to leave this as 12,2. You don't want to reduce this to 6 and 1 because the equality reflects what is written here, or the conversion factor reflects what is in our equality. These other ones, you would not want to reduce this 6 over 2 to 3 over 1. You want to insert the numbers based on the coefficients in the chemical equation. 3.5 times 12 divided by 2 is 21.0. Do we have to write the 0.0? Well, we're given three numbers here. The 12 and the 2 are exact, so whatever you're given, if that has three numbers, you want three numbers in your answer. And our final problem, what volume of CO2 is generated when you burn the 3.5 moles of benzene? Well, now we have to go back to the days where we remember inequality. 1 mole of any gas at STP takes up 22.4 liters. So we can put 22.4 liters of CO2 on top, 1 mole on the bottom, or we can put 1 mole of CO2 on top in the 22.4 on the bottom. This converts moles of a gas to volume. This is something we learned several units ago. But in the problem above, we realized that we are going to produce 21 moles of CO2. So our given is 21 moles of CO2. They want to know how many liters this is at STP. So which of our conversion factors do we want? Do we want the one with 1 mole of CO2 on top and the 22.4 on the bottom? Or do we want the 22.4 liters on top and the 1 mole on the bottom? Well, whatever unit we're converting to, liters of CO2 needs to be on top. The unit we're trying to cancel out, moles of CO2, would go on the bottom. So we take 22.4 liters of CO2 at STP for every 1 mole of CO2. 21.0 times 22.4 comes out to 470 liters of CO2. This is just using dimensional analysis, where we can set up a problem based on their units. These problems will set themselves up. It's also called the factor label method, where you set up your conversions so that the label you want to factor out is factored out and you're left with the label you're trying to find. Label is another name for unit. But we're just using stuff we learned earlier this year, and we're now incorporating a balanced chemical equation in the calculations. An area of chemistry where we use balanced chemical equations in calculation to do calculations is called stoichiometry. Our last unit of this year, Unit 9, is our introduction to stoichiometry. I thank you for watching.